All right, chemistry students, we're going to have 2 more videos on chapter 10. This video is really going to look at buffers. Okay, so we're going to define buffers. It shouldn't be that long, but there's going to be an equation that's a little complicated that you're going to need to memorize and we'll work with, and then we're going to review reactions with acids that we already saw in chapter 5. Okay, and then the last video for chapter 10, video 4, will be about titrations and reactions with salt. Okay, or salts as acids and bases. Okay, so let's actually think, before we look at a buffer, I want you to think about if I just had a beaker, just a plain beaker of water, okay, and I added 1 drop, so I'll just make it a big teardrop, and that drop was hydrochloric acid. That is one of the 6 strong acids that you needed to know. So if I added 1 drop of HCl, what is going to happen to the pH of that beaker? So plain Jane water, the pH is approximately 7. It's a neutral pH. But this is very acidic, okay? Hydrochloric acid, so this is 1 drop. You can even draw a little dropper here, okay? And you've added something very acidic into water. What is that going to do to the pH of the water? So this beaker now is basically going to be very acidic. Regardless of whatever the pH is, it's definitely going to be less than 7. Okay, it doesn't matter what it changes to, but the water doesn't do anything to resist the change in pH, and therefore this new beaker is definitely, the one on the right is definitely acidic. Okay, so buffers, what they do is they resist change in pH. Okay, how do they do that? Well, what's going to happen is whatever we're adding, whether we're adding acid or we're adding base, they're going to somehow absorb that acidic or basic component that has been added, and that's what makes them a buffer by definition. Okay, so the next slide, I try to add a couple GIFs in here, these little moving things, is trying to explain that. Okay, so this is supposed to just be a car. If you guys know, cars can sometimes leak antifreeze, which is not good. It's actually poisonous for dogs, but antifreeze leaking out of your car, like maybe onto your driveway, tastes sweet to dogs, so dogs will actually lick it up, but that's why I have this sort of poison skull here in this reaction. Is this supposed to be antifreeze plus the dog licking it up is poisonous ultimately because it's actually really acidic for the dog. Okay, so what the body does, it is poisonous to the dog if it doesn't get removed and corrected, but if a small amount were added, you could think of this balanced reaction where HB is actually hemoglobin. We saw that when we were actually looking at Le Chatelier's principle, and the antifreeze has added excess acid, so this equilibrium will shift to the left, and that excess acid will bind to the hemoglobin, and the hemoglobin will release the oxygen. That's what actually happens. The dog's hemoglobin is messed up and it can't deliver oxygen to the rest of the body. Okay, so, or to the appropriate components of the body, to the cells. So that's what buffers, what you're thinking buffers are doing. They're resisting change in pH. Okay, so that's why it says here, resist change in pH with the addition of small amounts of acid or bases. Okay, what makes a good buffer are weak acids and their partner conjugate base. So if I have HA, as long as it's a weak acid and his partner conjugate base, the A minus, that will be a good buffer. Okay, so oftentimes in the body and in lab, phosphate's a good buffer. Acetate is another good buffer used in the lab because it's a weak buffer, or it's a weak acid. Okay, so effective buffers will have equal concentrations of the HA and A minus partnership. Okay, they'll have equal concentrations of both components, because that way if acid is added, the A minus can help. If base is added, the HA can help. And I have a little animation in a couple slides that'll explain that, and I'll show you how does the buffer absorb the added acid or base. How does it actually work? Okay, So these are the words for how it actually works. The weak acid will neutralize an added base, and the conjugate base, A minus, will neutralize any added acid. That's what's going to happen. Like I said, the animation is in the next slide. But this is what the animation, the big animation, that the title is How Buffers Work, on the next slide and the following slide. But these two bullets are explaining what that animation is trying to show. So to have a complete buffer solution, keep in mind you're going to have acid HA. So here's acetic acid. The H is listed first for the acidic proton, and then C2H3O2 with a -1 would be your A minus. You're adding the conjugate base. Now the conjugate base in the lab isn't just the C2H3O2 minus, or the A minus, okay? There is going to be some kind of cation bound to it, but that cation isn't doing anything, so we don't really care about it right now, okay? And the concentrations of HA and A minus are important. The ratio of their concentrations are important for how well the buffer actually works at resisting pH, okay? The ratio of their concentrations, and then what those actual concentrations are for this pair, okay? So let's look at this animation. The whole thing occurs inside this box on the very, very outside, but the box is, think of it like a beaker containing a buffer solution. So that's why there's sort of water listed out here, because it's all occurring in water. But remember, a buffer has HA and its corresponding conjugate base, okay? And this is just the balanced reaction where instead of H plus, it's actually listed out as H3O plus, okay? So I'm going to remove my red here so you can see the animation. So in this buffer solution, let's pretend we add acid, adding H plus, regardless of what it is. Could be hydrochloric acid, any of the other strong acids, it doesn't matter. So adding H plus, that H plus is going to react and bind with that A minus, forming new HA. So in my animation here, we combine with A minus, it's already there. You see how the A minus concentration went down a little bit because we have formed new HA, but HA doesn't belong on the right, he belongs over on the left, so the concentration of HA went up. So here's the new situation. We still have the same items present that we had in the beginning before acid was added to the buffer, but now the buffer absorbed the H plus that was added, forming more HA, and now as a result there's a little bit less A minus. So you could see if I kept adding more and more and more acid, at some point you would run out of the A minus and you wouldn't be able to form any more HA, and at that point you will have added so much acid that the buffer is no longer working. And that's why the concentrations of HA and A minus are important, okay? Let's go back, next slide. Go back to the same beginning concentrations. We got HA, we got A minus, and let's add base instead. Just the hydroxide base. That is actually going to react with the HA, forming some A minus as well as H3O plus, but we don't focus on that concentration. Okay, so it's forming new A minus, but he belongs over here where the green block is. So we have a greater concentration of A minus. So this is how the base is absorbed into the buffer. Now you do not need to memorize all these steps. You don't need to memorize that base is going to react with HA and acid is going to react with the A minus, okay? But you do need to understand that this is how buffers work. They're going to resist change in pH to a certain point until so much either acid or base has been added, and then they're no longer effective buffers at that point, okay? Okay, and there'll be an equation that you can use to calculate the pH as long as you were given the concentration of A minus and HA, and that equation we'll get to in a couple slides, okay? So that's just how buffers work. We talked about in the second video about acid strength measured in Ka values as well as pH values, okay? And I went over what P meant in that video. A little p meant negative log. And if you remember the table from your book, the Ka values for a lot of weak acids are just some number times 10 to the negative, and then the superscript is a big negative superscript. So 10 to the negative 4, 10 to the negative 8, 10 to the negative 10. Those are all for weak acids. So if we don't want kind of ugly numbers that you see in the Ka, we can make a new P scale. And this is a common P value or P scale that we call pKa, okay? Just like pH, you need to know, is memorized negative log of the concentration of H plus. What do you think pKa is? Negative log of Ka. So this blue formula here you must memorize. It's on the important formulas for chapter 10 on that extra handout, okay? You also, we've already discussed that Ka, like a low Ka or a high Ka, sorry, here I listed high Ka means a stronger acid and a low Ka means a weak acid. It's actually the opposite with pKa, but pKa numbers are generally more normal looking. Just like pH numbers scaled from 0 to 14, they were more normal looking, they weren't scientific notation. pKa numbers are more normal looking as well, but you need to know that pKa, just like Ka, describes the strength of an acid, but it's going to be the opposite as the Ka. A higher pKa means a weaker acid, and a lower pKa means that it is a stronger acid, okay? So ultimately, what chemists did was they put this pH formula and the pKa formula and the knowledge of buffers being a pair of HA with A minus, they combined them all together into one formula that we call the Henderson-Hasselbalch equation, okay? So it's a formula that we use when we're working with buffers, okay? It's a difficult equation, and this is it in blue here, but you must memorize it. You already kind of know part of it, all right? So if you know pH, pH equals pKa, so that would be usually a known value. If you had a buffer, the phosphate buffer or the acetate buffer, you would have a known what the pKa is of that substance. It could be found in a table in a textbook. And then as long as you knew the concentrations of the components for that buffer, you could solve for what is the pH of this buffer, okay? What I have listed above the blue equation, okay, is what you already know from the other equations. Technically, pH is negative log of H plus, and pKa is negative log of Ka, okay? So the Henderson-Hasselbalch equation just reduces down these negative logs into the appropriate values. But if you were given, say, H plus concentration, and these values, you could solve for the pKa of whatever the particular acid was, okay? Because you could determine pH, you could determine this far right component, and then you could solve for pKa, okay? Because that would be your unknown following the algebra there, okay? I will say when you're solving this equation, you're going to want to kind of do it in parts, like do this division part and then take the log and have some kind of number, all right? And if you were given a pH, you could subtract that number, or if you were given pKa, then you could just do the whole right side of the equation, okay? So one comment about the Henderson-Hasselbalch equation, it has to do with buffer solutions, okay? It's going to relate the pH to the pKa of some specific acid, okay? This note at the bottom, when the concentration of A minus equals the concentration of HA, whatever the pH is of the solution is the pKa of that acid. And what that basically means is, go back to the Henderson-Hasselbalch equation in blue. If these two numbers are the same, then I'm just taking the log of the number 1, which actually equals the number 0. Log of 1 is 0, so therefore the pH equals pKa, okay? And scientists just use that in the lab. If these values are the same, we know we're in the pKa equaling pH zone for that specific buffer, okay? And this would be done for individual buffers in beakers in the lab, where you're measuring the pH of that substance in the beaker, okay? So here's a question, an example question that you would have using the Henderson-Hasselbalch equation, okay? So I'm telling you the concentration of acetic acid, which is my HA, is 0.0089 molar, and the concentration of the acetate, which is my A minus, is 0.0020 molar, and the question mark here is pH, okay? Now I'm throwing you for a loop here just to make it super clear. I'm giving you the Ka of acetic acid, so I'm not giving you the pKa, which means you need to get the pKa, and then you can plug into the Henderson-Hasselbalch equation. So I just abbreviated it H-H equation here. So this is the Henderson-Hasselbalch. This number here does not go directly into the Henderson-Hasselbalch. I have to take the negative log first of this Ka to solve for the actual pH. But what I did here is here's my negative log of Ka. So this is negative log of Ka given up at the top, the Ka. And that I know is equal to pKa. All right, and then I have the A minus over the HA. That's a common mistake. Students will flip that. They'll put HA on top because they forgot to remember that A minus goes on top. Okay, so keep that in mind. If I were putting this into my calculator, I would solve and get this number here, and then I would solve plus log, and I would get whatever the answer is for that division of 0.002 divided by 0.0089. Okay, and ultimately I got 4.11 as my pH value, okay, for this problem. So that's an example using the Henderson-Hasselbalch equation, and we've gone through what buffers are and what they do, okay? The next several slides are actually, 3 of them are copied from chapter 5, but now that we've spent a lot more time on acids and bases, I want to go through them. So section 10.12 in your book goes over acid reactions again, okay? So I want to re-emphasize, did I miss a slide? I want to re-emphasize reactions with acids. So I'm so sorry. Sorry, I keep flipping. We are on slide 48, okay? So the first one that we had learned was a neutralization, where you have an acid plus a base, and you need to know that it produces salt and water. You need to be able to predict those products, that it produces salt and water. Hopefully, recognizing that this is a strong acid and this is a strong base, you're actually getting familiar with who is the acid and who is the base, and you could see this in black and white, not in the colors, and you would very easily be able to predict the products, okay? It helps when you're trying to memorize what acids and bases do to use the abbreviation. So remember, if HCl forms H plus and Cl minus, to use this HA abbreviation, okay? As long as you have the appropriate charge, okay? So you could summarize a neutralization reaction like your book does, where they just put M for metal instead of B for base. For example, they put M for metal, and then you're forming Ma, whatever that salt is, and that's where you follow ionic bonding with the cation and anion and form the appropriate formula. Water is also always in the liquid phase, and then everybody else is aqueous in the neutralization reaction. Neutralization reactions are probably the most famous, popular reactions for acids, okay? I'll give you one more example, and then we'll do another acid reacting with fill in the blank, something else, okay? So here's neutralization with this base plus this acid, okay? So this is where you need to recognize the metal and the appropriate A minus, okay? The biggest mistake is writing the salt, Mg2 plus and Cl minus. Don't make MgCl. They make MgCl2 following the appropriate ion formulas, which is why the product, this is salt, is MgCl2, okay? So like I said, the common mistake is just to be like, oh, look, putting these guys together and just to write MgCl and not balance it correctly with the appropriate formation of the salt, okay? So make sure your neutralization reactions are balanced correctly. The other reaction was an acid, still here, HCl, with carbonate. We saw this same slide in chapter 5, okay? And the hard part with this was carbonate produces H2CO3 as sort of a middleman, middle ground, which isn't on this balanced reaction. And this guy splits up into carbon dioxide and water, okay? We talked about that when we did this in chapter 5, okay? But you have carbon dioxide, water, and then there's the salt. So you should be comfortable with writing the salt now. Water's really simple. The carbon dioxide is the hard part because we are splitting up the polyatomic ion, and most of the time we don't do that, okay? Here's another example of acid with there is carbonate here. He's bound with something else. In the top reaction, he's only bound with calcium. In the bottom reaction, there's actually 2 cations present. Okay, and we stared at this particular reaction for a long time when we were doing it in chapter 5. Still forms the same 3 substances, carbon dioxide, salt, and water. Okay, so here's a reaction. Before I show you the answer, see if you can solve it. See if you can put the carbon dioxide, the salt, and the water together correctly and make sure your entire reaction is balanced. I already have the 2 here, so you know you're going to have some subscripts and stuff. Okay, so here's the actual reaction. So now that you've got that in your head, we'll finish this video. Thank you for listening. The next video will be on titration as well as salts, properties of salts that are acidic and basic. Okay, and that'll be the end of chapter 10. Thank you for listening.